So again, as we mentioned last time, a reference electrode is always required. And so when we consider cell potentials, we're always going to be measuring versus a cell potential. So as long as we keep one interface constant, we can understand reactions and cell potentials at the other interface. And I think we mentioned last time that the standard cell potential is the normal hydrogen electrode. NHE, and if you look in all your tables of all your, in the back of the book of the cell potentials, they're always listed versus the normal hydrogen electrode. And the normal hydrogen electrode is physically constructed by a platinum electrode that's in contact with a solution phase that has unit activity of hydrogen gas and unit activity of hydrogen ions. And the EMF of this cell is always considered to be 0 at all temps. So measuring it, the half reaction of any cell with the NHE, we can always just make that 0 and consider that to be 0. Also, that implies that the reaction of hydrogen in solution plus an electron going to 1/2 hydrogen gas, the half reaction is also equal to 0. So those two systems are also 0 at all temperatures. And these are 0 by convention and definition, not by physical reality. We have to have some standard, and that's what they've chosen to use. Okay. Now, in all of the reactions that we've done so far, we've made some assumptions about the fact that the cell potential is going to be at unit activities, and that's not always a good assumption. In fact, it's a pretty poor assumption. Most physical cells that we can construct, it's either impossible or inconvenient to make all the quantities at unit activities. And so E0, as they've listed for half reactions, are for unit activities and standard state of reaction, reactants and products. So for example, we have a material like a lead ion plus 2 electrons in equilibrium with solid lead metal. We can have an E0 of equal to minus 0.125 volts versus NHE. And again, that would have lead ions at unit activity in solution. However, it's difficult to prepare such a system because often we need to prepare that in a physically, some sort of solution of some sort. And so, for example, a table of electrochemical potentials will often list a cell potential like this, where they would write down E0 prime and say that's equal to minus 0.140 volts in 1 molar perchloric acid. Versus NHE. So you notice the difference. We have 15 millivolts of potential difference according to the standard state and when we consider it in a physical solution, like 1 molar perchloric acid. Why is that the case? Well, because the lead ion can actually undergo some equilibrium with the perchlorate anion, there's actually a shift in the potential of the cell. So often we'll use the idea of formal potentials, which are simply cell potentials that have non-standard activities or concentrations. So in this case, because the lead is not, it has unit activities, but we have to specify a particular type of solution, that 1 molar perchloric acid, to indicate the proper cell potential, that's a formal potential. And in this case, whenever they do give you a formal potential, they are required to suggest all the appropriate solution conditions. So if you look in the back of your book for the cell potentials, you'll see a number of situations where they'll give a cell potential and then they'll also give you a solution condition with it. All the iron 3+ and 2+ couples have that particular kind of formal potential described. Okay, and also in biology and biochemistry, they'll use formal potentials. Actually, I noticed in biochemistry, they'll use formal potentials to indicate standard potentials at pH of 7. And so they'll be at a particular pH of 7. And they use that in a different way than electrochemists use formal potentials. But the idea is the same. The electrochemist definition of the formal potential will include the biochemist definition of the formal potential, but not vice versa. Okay. So we'll have in our book a table of half cells the standard potentials and also formal potentials, and those are all written versus NHE. However, as I might have mentioned already, the normal hydrogen electrode is not an electrode that you would normally use in the laboratory. In fact, the way it's defined, it's physically unrealizable. You actually can't make the normal hydrogen electrode the way they've defined it. So in fact, people use other reference electrodes that are based on, so they'll use a reference electrode that they can reference to the normal hydrogen electrode. So they'll make their measurements versus the normal hydrogen, versus some other reference electrode, and then can refer that back to the normal hydrogen electrode. We've already seen a reference electrode in the previous lecture, the saturated calomel electrode, and that is a very popular electrode, although it's losing some popularity because of the fact that it's got mercury in it. And for many cases, they used to be using them a lot in, say, pH electrodes, but now because of the mercury concern, they've stopped using them so much. But in normal electrochemical measurements, you'll often use a SCE. Another very popular one, in fact, it's becoming quite the most popular reference electrode, is this silver-silver chloride reference electrode. In contact with potassium and chloride ions, that sometimes is saturated, and sometimes it is not saturated, say at 3.5 molar concentration. Now both of those have very similar E0s, standard potentials, and that would be 0.199 volts, and these again are versus NHE. But this one with a 3.5 molar solution would be 0.205 volts. So you can see that difference in 3.5 molar KCl solution and the saturated solutions counts to about 6 millivolts of potential. Not a huge amount in analytical work, but in fact for precise potentiometric measurements it's very important. Why would we care? Why wouldn't you use saturated systems, for example? That's an easier system to prepare and maintain. All you have to do is have a silver chloride or potassium chloride solution that's in contact with a potassium chloride solid, and you'll have a saturated potassium chloride system. But actually it turns out that there's good reason for using the 3.5 molar potassium chloride solution. I'll just give you the reason for that is that there is a temperature coefficient. let's see, how are we doing here? Temperature coefficient. And for the saturated system of silver chloride, it turns out that the temperature coefficient is about minus 1 millivolt per degree Kelvin. And for the 3.5 molar solution, it's about minus 0.73 millivolts per degree Kelvin. In other words, there is quite a difference in the temperature change, of the potential change with temperature for the two systems. And it turns out to be important. For example, a lot of times you'll use silver chloride systems in, people use them in, say, living animals where the temperature might be 37 degrees centigrade. That corresponds to approximately a 17 millivolt shift from 25 to 37 degrees C. And so the saturated silver chloride is not as useful as the 3.5 molar ones. It has less of a shift in potential with temperature. The silver chloride is a very common one. There's a couple other ones that are used. One that's used a lot, especially in corrosion work, is this mercury sulfate electrode. And that's mercury sulfate in solution with a saturated potassium chloride or potassium sulfate solution. E0 for this one is 0.616 versus the normal hydrogen electrode. And in many cases, we're talking about reference electrodes that are existing in aqueous solutions. Sometimes you'll be doing experiments in non-aqueous solutions, and so another reference potential that people sometimes use is to use the silver ion at say 0.01 molar silver ion in acetonitrile, for example, can be calibrated, and you can use that as a reference point. It's not a reference electrode, actually. It's just a reference point that you can measure against. So reference electrodes have a fixed potential. This one doesn't have a very fixed potential, but you can actually calibrate it versus standard potentials of other systems in that solution and get a reference point. Somebody asked me last time in class, how do you convert from a potential made versus a normal hydrogen electrode and a potential measured versus some other reference electrode. And so, for example, we might have the iron 3 plus an electron in equilibrium with iron 2 plus, and the standard potential for that is 0.77 volts versus NHE. And this would be appropriate, for example, this would be this sort of cell. Okay, so when we measure this half cell reaction, we're essentially measuring it versus the normal hydrogen electrode. And so how do we do that? Well, that's a reduction, so that's 0.77 volts versus NHE for this particular case. Now, if we put in say a silver chloride electrode, how do we calculate that cell potential? The same way as we would calculate versus the NHE, remember we would write those as always. We can add them up. And we can put in our silver chloride system. Now we're writing silver chloride is a oxidation now, so we're going to go silver plus chloride ion going to silver chloride, there's no plus an electron. And if we remember what I wrote, we said that in this particular case, for a saturated one, it would be 0.199 volts versus a NHE, but since we've written it as a oxidation, we will have minus 0.199 volts versus NHE. Okay. The 0.199 volts versus NHE is written as a reduction as normal, and that would be the half reaction. But since we're writing this now as an oxidation, we're going to write it as the EMF will now be switched to the opposite sign. So again, we would add those up, and it would be 0.5671. Is that right? Something like that. Volts for that particular cell. So that would be how you convert from any one to the other. That's a little complicated. I think an easier way to do it is just think about it as a timeline or a potential line, if you like. If we have 0 versus NHE, we can think about our iron as being out here at plus 0.77 volts versus NHE, and our silver chloride at plus 0.199 versus NHE. Okay, and so we can easily see that if we measure this potential versus here, that's 0.77 volts, but if we measure our iron versus the silver chloride, it's going to be less, 0.571 in our case. All right? So that's a more intuitive way of thinking about what the potential will, how the potential will shift if we use different reference electrodes. All right, so the book has more discussion of using the Nernst equation to calculate cell potentials. I think a lot of that has been done in previous chemistry classes, so I'm not going to have you, I'm not going to sit through and do it. You can work through that yourself, I think.